Thank you very much for the kind introduction. So I am going to cover some works, a couple of works on LLM safety and security, and basically, like in the introduction you gave, I work mainly in the multimedia area, and we have been working in this area for a very long time. We started looking into multimodal models and vision language models, and that's how we got into language models. So I'm going to present basically two pieces of work today, and one is going to be very empirical, and the other is going to be very theoretical. And this is a couple of the recent works in my group. And one is on adversarial vulnerability and the other on hallucination. Okay, so I think broadly speaking, again, I have a lot to cover, so I'm going to kind of rush on many things. I think from the safety and trustworthy challenges, I think there are, broadly speaking, in the use of LLMs, there are two aspects. One is what I would say innate, which is the problem with the model themselves, and the other is the misuse. And the misuse is how can models be misused for various purposes, typically misinformation, disinformation, or even creating malicious code or any such things. But today's talk, I'm going to focus on some of the innate challenges. And I think the reason for innate challenges is the innate limitations will not go away by just using some simple tactics, just like increasing training data or increasing the model complexity. And as I said, I'm going to present two of our works. One on LLM can be profit to fool itself, and the other thing was about hallucination. So let me just get started. So this was the work which was done basically by my PhD student Xie and former PhD student Jing Feng and a bunch of collaborators, and we had presented this in IEEE earlier in May. So we have been working in our group on adversarial machine learning primarily with images, and so there's a rich body of work on adversarial attacks as well as adversarial training for images. And we were kind of getting curious about the language models, and that is what kind of motivated us to do this work. So effectively, we all know that LLMs can do zero-shot inference, and one of the classic things is, say, for example, we want to ask the LLM to predict the sentiment of a sentence, right? So we can say that the tone of the sentence is either positive or negative. Right? So this is the usual sense. So the idea was that in both in image classifiers and in general vision models and all, we want to test the robustness of LLMs. And the robustness is very important because if you're going to deploy these large language models, you have to have some confidence that they're going to work, no matter how the inputs come. So I think there is, as I said, in images we do a lot of the adversarial training, and there is the adversarial robustness, which is so there's a natural accuracy and the robust accuracy, which are two important measures on the robustness of the model. So how do we done normally? So we take an original data set in images, and what we do is we created adversarial samples. And the standard method, for example, in images is to use PGD, projected gradient descent, and then you create adversarial samples. Okay. So and that is a very nice way of doing it. So the question was, how do we create adversarial samples for LLMs? Now, it turned out a little bit of history that there has been a lot of work in NLP on adversarial attacks on NLP long before LLMs. And typically, I think the LLM work was usually there is an original input, there is a sentence, and then there is an attack objective. And the idea is that you take a sentence and, for example, you want to do misclassification or you want to predict the wrong sentiment, then you do some perturbation to the sentence. And the perturbation could be a character level perturbation or a word level perturbation or even paraphrasing. And the idea is you do it in such a way that the semantics is preserved, but then the model is fooled into giving the wrong classification result, for example. Right? So that was the whole idea in NLP. Now it turned out when we started looking into this, there were two existing methods for LLMs, which was the AddGlue and the AddGlue++ method. So again, I'm going to skip a lot of the details. Typically, how they work is you have a test data set for which you want to create an adversarial test data set for robustness testing. So basically, you need an ensemble of language models and you need the white box models because you want to play around with the gradients. And basically, you want to use those white box models and then create adversarial samples, which you can use it for a target LLM, which could be a black box model. It could be a white box model or a black box model. There are two problems with it. It is computationally expensive. That in fact, to create, for example, the latest work at AddGlue++, to create an adversarial sample takes 330 seconds to create one. So that's very, very unacceptable. And the second problem was the existing robustness evaluation is not very effective. And the reason is that the adversarial samples are not specifically created for the target LLMs. They're created using some other large language models for which you need the white box models. Okay. So this was our motivation that given that these are the two limitations of the existing ways of creating adversarial samples, how do we effectively and efficiently evaluate the robustness of LLMs? And we want to create quickly adversarial samples. Okay. So basically, what we did is a very simple idea. I mean, we basically converted the conventional NLP adversarial attacks into a prompt-based adversarial attacks, which we call the prompt attack. And the idea is extremely simple. Basically, what we do is there is an original sentence and there's an attack prompt, and basically we just ask the LLM itself to create an output for which it will fail. Okay, so you ask LLM to fool itself, and we basically kind of tried it. Does it work? And surprisingly, it works. And it basically the computational cost is very low. And the second thing is you don't need any white box models. You can do it for a black box model as well. So then we started refining this method, and basically we kind of made it very systematic. That you have an original input, which is your original test data set, for which you have an attack objective, and then you give an attack guidance. And the guidance, again, we took inspiration from NLP, the pre-large language model based NLP attacks. Basically, there are different types of changes at the character level, word level, and sentence level. These are the guidance we give. And then basically feed this back to the LLM for which you want to generate the adversarial sample. Okay? So it turns out that it worked quite well, and then we basically found that there are two kind of strategies. One is a few shot strategy, that is in the attack guidance you give a few examples. Right, basically it's to do in context learning. You give, and we found that giving 5 samples is sufficient. You give 5 samples. So basically you do that. Or an ensemble strategy. Basically you collect an ensemble of the adversarial sample and give them all possible distance and try the perturbations. And of course there is a way that you want to make sure that the perturbation preserves the semantics. So we have a way of checking for the semantics is not altered, and therefore it is indeed an attack. It's not some garbage computer. So again, to give you, I'm skipping a lot of details. You can see that for the attack success rate, that is the usual measure. Typically for a Llama 7B model, the past attacks were about 37% and ours was 50%. So overall, there's a substantial jump in the attack success rate. So significantly, we are outperforming the state-of-the-art methods. So this is a very simple thing where you use the LLM to attack itself. And not only that, we checked on the effectiveness. That means how good are these adversarial samples. So ideally, in an image world, the adversarial image should look exactly like the original image. And in this, for adversarial attacks on LLMs, you want the adversarial sentence to semantically be almost or the same as the original testing sample. So basically, what we found is that the prompt attack can generate adversarial samples of very strong attack power and of very high fidelity. So this is a very cheap way. So as I said, AdBlue++ takes 330 seconds to create one adversarial sample. We need only 2 seconds to create one. So it's a huge improvement in the computational efficiency. Okay, and these are some of the samples. I'm sorry, the font size is a bit low, but we can kind of skip the details. So the idea is, as I said, we need to do robustness testing of LLMs, and what we have found that now that we have a very principled way of generating a large number of adversarial samples. And the next thing what we are going to do is, which is our current work, is how do you do better adversarial training. Again, what we are trying to do is there is a rich body of work, including our own group's work for adversarial robustness of vision models, and we are going to see how we can use some of these ideas for language models. Okay. So and hopefully in the process can make more robust LLMs. Okay, I'll kind of finish. This is the empirical work which I wanted to present, and the next piece of work is more theoretical, and this is the work about hallucinations. This work has been done with Zive, who was my former PhD student and current postdoc, and we have him in our audience right there, sitting in the second row that side. Yeah. So this was work done with Zive. So actually it started with conversation between me and Zive, and then we found that it would be useful to include a colleague. Sanjay is a colleague in computer science at School of Computing and NUS. Okay, so we all know what are hallucinations, right? I mean, that has, with Gemini, I think it came into renewed So hallucination is plausible but factually incorrect or nonsensical output. They are plausible because they are grammatically correct and you can comprehend, but they are factually incorrect, right? And in fact, if you do a conversation, there's a lot of examples of hallucination. I will not go into that. I think all of you probably are familiar with many of the examples, but I think it needs attention. It needs attention because now people are talking about serious deployment of LLMs in areas like in finance, in medical advice. People are thinking of deploying LLMs, and if they are used in such class, we better hope that they don't hallucinate, right? So I think it is very important to study this problem, and more importantly, I think Zive and I were talking, and we said some formal discussion is necessary because we saw there's a huge amount of work on hallucination, but they are all about very empirical. They are about improving the training data or changing the architecture or putting different types of prompt, but there was not really any formal work. Though we found that there were a couple of related tangential works, but they were kind of very initial works and not so good. So what we decided is we should be making some more formal, rigorous statements. So the real intellectual question was, what task can LLM surely be trained to be hallucination? And more importantly, the general question which we were asking is it ever possible that we can completely remove hallucinations from LLMs? Okay? So that was our trigger and motivation for doing this. Okay? Now, formal discussion is very difficult. Why? Because, what do you say something is truthful, right? Semantics is very hard. So what is fact? What is correctness? In fact, philosophers have struggled with the notion of what is truth for thousands of years. And in fact, there is no consensus yet on what is truth. Okay? So the question is, given that with natural language, LLMs are great at natural language, where you cannot characterize truth, how do you go about characterizing or formalizing hallucination? Well, so what we did is, okay, since we can't do this in the real world, which is very hard, really smart philosophers have been trying for centuries and they have not succeeded. What would mere couple of computer scientists do? So we said, okay, can we find a subset of the real world where facts and correctness can be easily defined formally and contains reasonably many real world problems? So that is very important. Okay? And it turns out that it was not very too hard to find. The subset we chose is the formal world of computable functions. And this is what we computer scientists have been doing for a long time. Right? So what we now do is, a fact is defined as an output of a computable function. Okay? So, and the interesting thing is, a fair portion of the real world problems are computable, right? I mean, that's the whole Church-Turing hypothesis, that many reasonable things in the world are computable functions, okay? And it is, in fact, the underlying basis of computability theory and complexity theory. Right? And there is a lot of tools out there. And you know, you can view LLM as a next local prediction, and that's a computable function. Right? Okay, so LLM in the formal world, LLM autoregressively completes a partial input sentence. So LLM effectively is a computable function page that extends a string of tokens, right? And basically given an input from, we want to create the output. And the output should be such, so this is a computable function, but it has, the output has to satisfy certain properties. And basically we wanted it to be natural language, right? As how we converse. Right? So that is our usual notion. Okay, so basically now, if your whole world, instead of the real world, is the world of computable functions, then it is very easy to formally define what are hallucination. Hallucination is nothing but an error in the formal world. So what we can do is, if there is a computable function, f, and you give an input s, any string, and so there is an f of s. So if you give s, if you get f of s, then that's a truth. But if you give s, and what the output is from the LLM, which is not equal to f of s, then that is an error or an hallucination, right? So anything which is a false answer to the computable function is a hallucination. So now we can formally define hallucination in this formal world that an LLM-H, which is a computable function, by the way, is hallucinating with respect to some ground truth function f. This is the f we are training the LLM to learn, right? So we are trying to train the LLM to learn a computable function, okay? And then after the training, you give an input s. If it produces f of s, then great, it has learned the function. However, if it does not produce f of s, then it is hallucinating, right? And then of course you can say, you're talking about computable functions and you say that's an LLM, Well, to be very honest, even the grammars and the nationality, they are all computable problems, they are all computable functions, and grammars are also computable functions. So languages are actually computable functions, though the facts are not, because what are facts is very hard to say, right? Therefore, we stick to computable functions. Okay, so this is our, now in our world, the subset of the real world of computable functions. This is how we see the real world, and we saw in the previous talks, you have a corpus and you basically use the corpus to train an LLM. So here, in our formal world, we train LLMs by training samples which are S0, f of S0, S1, f of S1. So there's a whole bunch of training data. And you can actually create any amount of training data with any computable function, right? And then the training part is you take an initial LLM with random parameters initialized. And then you take S0, f of 0 and you update. And in fact, what we say is you can train it with 1 sample, 2 sample, 3 sample, infinite number of samples. You train any number of samples. So in this formal world, we say you train as much as you want. Okay? But at any point in time, you say, okay, I've trained enough. And then this is my LLM, this is my trained LLM, then I want to check for hallucination. So I give a new input S, and is h of s f of s, because this was the f which was used to create the training data, right? If it does, then it works. If it doesn't, then it hallucinates, right? So this is a very nice handle on the whole hallucination problem. So then we were asking a fundamental question. So we have assumed LLMs to have a finite computational complexity. They are computable functions. In fact, they can consume infinitely many training samples, and they are actually powerful than any existing LLMs. So the fundamental question really now becomes is, can these formal world LLMs be trained to be hallucination free? Okay? And why? Because if yes, then of course LLMs can solve a large family of reasoning tasks, in fact a whole bunch of computable functions. But if no, then LLMs will inevitably hallucinate, which means that there are some very serious implications of LLM safety in real world deployment. So whether LLMs can be trained to hallucinate or not is a very simple question. For any ground truth function f using the training samples t, can an LLM h be trained such that for any input s belong to the set of strings, is h of s always equal to f of s? If it does, then it is hallucination free. If it is not, then it always hallucinates. Okay? Well, the bad news is hallucination is inevitable. And I'm going to prove it. I'm going to theoretically prove it. Okay. So that is the inevitability theorem, which means we will prove that all computably enumerable sets of H, that exists a computable ground truth function, that all of the trained LLMs will always hallucinate. It's a very strong result. Okay. Now remember, H of ij is an LLM H which is in a state after being trained on S0, f of S0, S1, f of till J samples. And interestingly, the proof of this fundamental result is surprisingly easy. And we do it by construction, okay, which is using the Cantor's diagonal argument. Okay? So we do basically a diagonalization proof. Now, to remind people about high school math, Cantor made this brilliant discovery that they were used to show that some infinite sets are uncountable. And this is a very simple example that you want to show that all infinite length sequences of binary digits is uncountable. And how do we do that? We assume the opposite, right? We assume that they are countable. That means we can list them. So we can list all the set of binary sequences, right? So if you do that, you have a nice infinite, countable infinite list, okay? So let's assume that we create a list of all elements, and this contains all possible binary sequences. Well, then what you do is you take the diagonal of this list and you flip each element and you create a new string where the first element differs from that first string in that list, second one in the second, right? So this constructed string is different from each and every element of that list, right? And so now there is a contradiction. Why? Because the new sequence is not in the list, but it is the set of all binary digits. And therefore, what was wrong? That our assumption that this set was countable was wrong, and therefore this set S is actually uncountable, right? And we had encountered this in high school, different variations of this. We can use the same argument here, okay? So how do you use the same idea to show that hallucination is inevitable? Okay, so actually we build up into a series of more and more complex theorems, but I'm just going to give the simple ones just to give an intuition. Okay, so assume there is a set of LLMs. Okay, for any particular F, at least one membered LLM is hallucination free. Right? We need to make this assumption that one LLM is hallucination free, because if no LLM is hallucination free, then the theorem is trivially proved. All LLMs hallucinate, right? So there is at least one. Okay, and then what we do is we want to now list all the LLMs in this set that we index by two integers, I and j, right? J is the number of training samples, so we will basically use a Cantor pairing index to list all the LLMs, which means LLM1 trained with one sample, LLM1 trained with two samples, and so on, then LLM2 trained with one sample, two samples. So we list all possible LLMs, okay, using this Cantor pairing. Okay, so that's what we do. We assume that there is a set of computably enumerable set. So I'm starting with a restricted set of LLMs, which are computably enumerable set. And these computably set of LLMs are there. And these are the outputs for each of them by assumption. And we say there is at least one LLM which is hallucination free, and this will have all possible f of s, because we list all of them. Then we do the same diagonalization trick. So here the diagonalization is such a way that for the first LLM, we create this a new computable function delta of h of s0, which is just said that it is a different string other than the one LLM1 produces. And then similarly LLM2, LLM3, LLM4. And therefore f is computable because both the delta and h of I are computable. And f of si is not equal to h of si for any I, so f is not index. Which means the assumption that there is at least one hallucination free LLM is wrong, right? So there is a contradiction. And therefore, basically, since this contains all possible f of s, this particular f is not there, and therefore there is a contradiction, and therefore this assumption is false and the theorem is false. Okay. Of course, this was computably enumerable sets. We can now extend it for their now. Okay, so this what this result really proved was there is at least one input on which each LLM will hallucinate. Then you'll say, what's the big deal? In a real world LLM, there's only one input on which it can fail. Then it can still be useful. If all the other infinite inputs it can work, so is good. Well, the bad news is we can actually extend the argument for computably enumerable sets that each LLM will hallucinate on infinitely many inputs. This is a slightly more complicated argument. Is that you list a set of LLMs and then you construct a new f of delta, but it is slightly different where the delta of HSI is j less than I. That means it is different from all the S1, S2 till I is less than j. So it returns a different string for the first j for this, which means that For S1, it will hallucinate, from H0 it will hallucinate from S1 onwards. For H2, from S2 onwards it will hallucinate. So there's a whole bunch of different. So there is no hope. Each LLMs will now hallucinate on infinitely many inputs. Okay. By the way, this is completely theoretical proof. All we say is there is an existence of a computable function. If you give me an LLM and tell me which computable function is this, I cannot tell you, right? Because this is just an existent proof. There is no, it's not a constructive proof. Yeah, this is an existence proof. Okay. But the upshot is that any computable LLM will hallucinate in some formal world. Any formal world is a subset of the real world. Therefore, any computable LLM will hallucinate in the real world. Then, of course, do we have real-world examples of for real? So then basically, the question we asked us, what does it mean for the real-world example? Okay. So now, f is a computable function not computable by LLMs. And what problems cannot be computed by real-world LLMs? So I think this kind of gives you some idea. This is the set of total computable functions within which they are computable by theoretical LLMs, the kind I described. And then there are the computable by the real world LLMs. Now, in theoretical LLMs, the number of training samples is any finite number, and the model complexity can be any finite complexity. Right? In the real world, there is physically limited number of training samples, and of course, there are physical number of parameters which can be used by on the computer. So what we did is very simple. Again, we have much more details in the paper. If you have a polynomial time complexity LLM, it cannot combine combinatorial lists because a simple task, for example, if I give you strings A, B, and C and say, tell me list all the lists of combinatorial strings of a certain length, say length 10, of all the combinations of this A, B, C. Okay, this is something which is very easy for us to do. But LLMs will fail because that's an exponential problem. So any combinatorial list cannot some finite length alphabet is exponential, so it cannot be done by a polynomial complexity LLM. A Presley curve arithmetic cannot be done because it's double exponential. And assuming P is not equal to F, then basically Boolean satisfiability cannot be computed by an LLM. So in general, actually there is a very strong result we have in our paper, which is general computer cannot learn all computable orders. And this is serious, right? Basically, what we show that a linear order is an abstraction of many real-world tasks like chronological order of events, sorting, and many other things. And basically, we show actually as a proof that LLMs cannot learn all computable linear orders. Okay, and basically, it's suppose you map 1 to A and 0 to B. So 1 0 0 becomes A B B, and then you can do some linear ordering of the binary strings, and you can give such an example to the LLM. It actually cannot learn, and we did experiments, two kinds of tests. Let X be a string and Y string, and what do you return, and two types of tests where you give example orders from 0 to M and excite Y in the examples, but the relation whether it's less than or greater than is not there, and the correct answer is the order of X and Y. Or you give example orders from 0 to M and at least one of X and Y is not in the examples, and the correct answer is the order of X and Y, or I don't know. And turns out that all LLMs fail. All LLMs fail on the simple task. Okay. Now what really it points is that we need a very principled approach to understanding the power of LLMs. What we think as humans is difficult, which is to create natural text, we think it's a very difficult task. LLMs can do very well. But something simple, what we think of, is to create combinatorial examples of strings, which we think, given a paper or pencil, all of us can do that. But LLMs can't do it. Okay. So that is a very interesting and a somewhat counterintuitive design. So the only key assumption we have made is the LLMs learn from input-output pairs. The following may reduce, so I think then our original motivation is, can we really create a hallucination-free LLM? Turns out that the following will reduce the amount of hallucination but will never completely eliminate hallucination. That is using larger models and more training data, or using ensembles of LLMs or chain of thought or any such kind of method. Okay? And we have made no assumption about the architecture or anything about the LLM. However, the following will reduce, like guardrails and fences or RAG, will reduce because these are methods which provide information beyond input-output pair for the training. But again, we really have to see what are the power and what is the scale. So these are some very interesting observations. I think what are the practical implications? I think LLMs, as we know, are very useful. Because if LLMs produced only nonsense, we would not have this workshop, right? They are very useful. But the question is, they also fail. And they can fail in very subtle ways. Though I cannot tell which LLM will hallucinate on which function. If you don't know, to me it's very dangerous to use in a situation which is safety critical. Okay? And therefore, one of the important things is LLMs are not general problem solvers because of the inevitability. And we need to have guardrails and fences because the hallucination will happen. And the question is, I don't know when, I cannot predict when. One has to be careful. And therefore limit the applications to the realms where the risks are acceptable. And therefore, in my opinion, I think there is a lot of very interesting and exciting empirical work, but I think there is a little bit of balance needed by some more theoretical and formal work, trying to understand what are the LLM's ability boundaries. What can it do? What can it do? Cannot do. As I said, problems easy for humans might be difficult for LLMs, and therefore intellectual difficulty for us does not mean that there are computational issues, and vice versa. And some more practical information. So I think we very strongly advocate that LLMs should not be automatically used to make decisions on human life or rights and properties, or provide suggestions on sensitive topics to uninformed users, for example in law, in medicine, in customer service, and robotics. And then we are seeing already problems related to that. Okay? They will unfortunately hallucinate. And this also leads to some very interesting open problems on assessment of models' capabilities and vulnerabilities, and assessment of task complexity and safety. And let me a little bit elaborate on this. So assessment of models' capabilities. So how likely, unfortunately these are nice theoretical results, but if you bring an LLM to me, is how much will it hallucinate? What is its propensity to hallucinate? I don't know. My result doesn't give any information. Currently, what is the best we do is, we use some test data set and empirically evaluate against it. There are two problems with this. One is does this test data set is really capture the underlying computable functions? Most probably no. And I think it cannot. The second thing is that the next iteration of the LLM will ingest this data set, and therefore it will stop hallucinating on this benchmark. So you have to constantly create new benchmarks. To me, one of the problems with this benchmark is they're done by tasks, which human beings are interested in. I think there has to be another dimension there, is the computational complexity of these tasks. And can we create a hallucination benchmark data set, taking into account the computational complexity of those tasks? And I think nobody has done that. There's an open thing waiting for. And how easily can the model be attacked? And how to generalize the vulnerabilities across data sets. As I said, in terms of adversarial attacks, I think the test samples are finite, but the attacks are evolving, and there are black boxes, and you cannot detect vulnerabilities just by doing one. And therefore, I think it is very important for efficient and principled detection of the vulnerabilities, and understand models' weaknesses. Hallucination is a big problem. Robustness is another huge problem. As I said, task complexities and safety boundaries. What are the complexity of tasks? For low complexity tasks, how to ensure LLMs can complete them? And what is the relationship between the task complexity and the model model? Again, these are not been explored. Okay? And determining complexities for the real world problem is not always easy, and also verifying for black box models is really hard. But this is extremely important because to use LLMs wisely, let them solve what they can really solve. Right? For example, we all use calculators. Calculators are great because you punch 3 times 4, it will give you 12. You punch a large number times large number, it will give you a large number which you can trust because that algorithm works. And if you put a very large number beyond the precision of the calculator, it will come up with an error. But LLMs will always give you an answer. You can't trust that. And the thing is that many of the hallucinations are obvious and we laugh at them. But what if you are a financial analyst, you are ingesting a lot of reports, and there's some subtle hallucination out there inside. And there's a whole chain of business process built upon this. Then I think there is a serious issue. Because you cannot predict where the hallucination will happen. Right? And therefore, I think we advocate we should use LLMs what they're good for, and not use LLMs for which actually you can build a special purpose program which you can trust, you can verify, right? So and I think this is what the state of the art is evolving into, using a combination of LLMs and other tools, and which is I think the right way to do. Finally, as I said, do we want one LLM or AI model for various tasks, or an LLM AI model that uses different external tools for different tasks, and or an LLM AI model for a specific task, where which we can make some theoretical guarantees of its performance. And of course, there is a complicated trade-off between the safety and the utility, and also there are different beliefs and ideologies on AI's future and the notion of some real risk or existential risk and many risks. So I think this is very important because vulnerabilities will vary when the models are tasked differently, and the deployment of LLMs actually has serious societal implications. So with this, I would like to basically come to my last this thing. One thing I want to remind, I think in this hype of LLMs, I mean, this crowd, I think it's not a problem, but in general, when I talk to general crowd, I think there's a lot of hype and excitement of LLMs. But I think we have to remember that LLMs are computer programs. That means all the results from complexity theory and computability theory apply, right? And therefore, I think we should try to use the insights which we have known for a long time. And therefore, there are some innate safety challenges like adversarial vulnerability and hallucination, and they require substantial efforts to fix or even to understand. And therefore, I think we need to continue the empirical studies as well as formal studies on LLM safety and ability boundaries. And I think what is exciting, as many of the previous speakers pointed out, there are many open problems in this area to work on, depending on your predilection for very empirical work, or very theoretical work, or a combination of them. That's all I have to say. Thank you.